By the standards of today, 1968 was a medieval time of communication technology. Typewriters, not word processors, pounded out letters. Most telephones used rotary dials. Black and white television was as common as color. The height of high tech was the lunar module, which had less computing power than today's personal computer. 1968 also was the year Larry Roberts sought out the engineers to build the Advanced Research Projects Agency's computer network, the ARPANET, the acorn that would grow to become the mighty Internet. It was going to be based on special-purpose mini-computers called Interface Message Processors, or IMPs, and a revolutionary technology called packet switching.
So here's the way it works. Suppose I want to send a long document. I feed it into the network. The first thing the network does is chop that up into a lot of little pieces called packets. And each packet is launched into the network, and it tries to find its way to its destination, each packet operating independently. At the other end, the final destination takes all these packets, think of them as little postcards carrying your data, puts them back into a long document, and delivers them to the recipient at the other end.
The plan was to network 4 identical IMPs. Each one was to be attached to a different kind of mainframe computer, a Sigma 7 at UCLA, an s9e48 at the Stanford Research Institute, an IBM 36075 at the University of California at Santa Barbara, and a PDP-10 at the University of Utah. Roberts asked 140 companies, including AT&T and IBM, to bid on the project. But the giants of communication and computers refused. They said it wouldn't work.
No, they didn't think it would work. They didn't see that it was very important or mainstream. I mean, after all, communications, well, we've got our own communication systems here at IBM, and AT&T does the telephone system. What else do we need? What's your problem?
So the telecom guys would say, little boy, go away. You represent no revenue to us. And they were right, we didn't. So little boy went away and created packet switching on its own.
A small Cambridge, Massachusetts company, Bolt, Beranek and Newman, known as BBN, wasn't sure either, but they were willing to try. Frank Hart headed the BBN team.
Well, we had to, first of all, figure out if we knew how to do it. I think it was a relatively revolutionary concept to put together a packet switching communication system, and no one had done that before.
BBN won the contract and went to work building the IMPs for the ARPANET on January 1st, 1969. The first was due at UCLA in 9 months. Hart's team faced a crush of obstacles and very little time.
It's not like a scientific discovery of the second law of thermodynamics or finding what DNA molecules look like. It was an engineering problem with dozens of very difficult, messy, undone engineering problems. And some of them were simply the fact that it was such a rushed schedule.
UCLA was also under a deadline to write the software so its Sigma 7 computer could communicate with the IMP. Ironically, graduate students were chosen to forge this first important link in the world's first computer network.
The senior professors who were in charge of each of the projects, the principal investigators, as they call them, really did not spend much time thinking about or focusing on it. It was left to the next tier down, to the graduate students or in some cases staff members at places like SRI. Just figure out something useful to do with this.
Crocker wrote the code to join UCLA's computer to the first IMP in what was to become the ARPANET.
The idea of having one computer send a program over to another computer was a big leap in some ways, but very natural in other ways. But in those days, there was no commonality across the computers, and so part of what we had to think about was in order to make that idea work, there would have to be a common language, and we actually spent time trying to define what that language might be.
Back at BBN, Hart's team was facing numerous engineering challenges. One was, how do you stop the packets from circulating forever? How do they know when to stop at their destination?
You dump a piece of message into the system, and now it's to wend its way through it, at each node picking the best path. Well, what stops it from circulating forever? That was a very difficult technical problem. No one had done that. Another thing, a host has a big message to send. It dumps the big message in. What stops it from overflowing? What protects the system from just having this stuff fall on the floor?
And there was a concern about the phone lines. They were built for voice traffic, not data. Special hardware and software was required so that when errors occurred, the imps could retransmit the message. Also, there was no guarantee the mainframe computers would hold up. They were just not built to run non-stop as communications machines. Even worse, how would you know where problems were occurring to fix them?
When some guy in some site hit a key on his keyboard, the message had to go from his keyboard to his big computer, from his big computer to the little computer, through a whole bunch of other little imps at other sites, and finally to a one at the destination, and then into the host, and then it had to come back all the way. And when the guy didn't get an answer, he didn't care where it broke, he just didn't like it. He kicked it, you know, he would yell and scream. So you had to have a way of finding out where it broke. And that was, again, a difficult problem for the network authority, which was us in this case.
There were glitches up until the day BBN shipped the first imp to UCLA. In fact, BBN could have kept on improving it forever.
I mean, there were people in the group that wanted it perfect, and there were other people that said, come on, we gotta get it out of here in 9 months. It has to be just good enough. That was a kind of decision that I ended up having to make. What was good enough, and where did one seek more perfection?
On September 1st, 1969, the first piece of hardware created for the computer network that was the forerunner of the Internet arrived at UCLA.
What I do remember is that they slid the thing in place, turned the power on, and the lights immediately started blinking because the program had been put in when it left, before it left BB&N, and it was just turned off. When they turned it on again, it picked up right where it left off. Now, there wasn't much of a network to speak of. I mean, there was the first node at UCLA. They didn't have anybody to talk to, so we just sent traffic to ourselves.
By the end of 1969, all 4 sites were interconnected. Had this primitive computer network failed, the effort to network computers might have been scrapped as just another project beyond the reach of current technology. But it worked. In April 1971, the ARPANET had 18 mainframe computers hooked into the network. Bob Metcalf was a grad student who connected MIT's computer to it.
The thrill was connecting things together. You know, there's action at a distance. How, you can wiggle something here and it moves over there. So I was able to form packets of bits and send them. And over the phone, the guy in California would say, I got it. And I'd say, well, send it back. And then he'd send it back. And it was the thrill of reaching out and touching someone or something far away.
At first, there wasn't much to do on the ARPANET beyond transferring data files among its members. But then, a new capability was added, the first killer application that would bring in the masses and take the usefulness of computer networking to a new level. That killer app was email.
I was actually working on a mail program, but it was programmed for a single computer so that you could send messages from yourself to another user on the same time-sharing computer. And I had written a couple of programs to transfer files, and it occurred to me that since the mailbox that I was sending these messages to was nothing more than a file, I could send that file across the network instead of keeping it within the same machine. And so I put 2 programs together, modified the code a little bit, and the first email program was created.
Tomlinson did more than just write the code for email. In a keystroke, he gave the world a new icon for the information age, the @ sign.
The @ sign was the most obvious choice because we're talking about a user who was at some computer, and it just made sense.
Ironically, what would become one of the most popular applications on the Internet was a program Tomlinson wrote on his own time.
It seemed like a neat idea. Nobody was clamoring for email. I mean, there was nobody, our sponsor, Department of Defense, didn't say anything about wanting email. My boss didn't say anything about email. But in fact, nobody said anything about email because the term wasn't coined until several years later. But it just seemed like an interesting thing to do with a computer and a network. And so I just did it.
So then electronic mail became the completely unanticipated killer app, as we say, for the ARPANET. We went from remote login, file transfer, electronic mail in a year flat or 2 years flat. And then it stayed that way for 20 years.
In October 1972, ARPA turned science fiction into science fact when it demonstrated the computer network in Washington, D.C. But unlike flying saucers, this idea really did take over the world. Due to censorship, it was not until 1999 that internet access became available to the Saudi Arabian public.